There are many things you take granted throughout your life. Things you do every day without appreciation. For example, you might call your mom to pick you up after school. How would you do this 200 years ago? There are no phones, so what do you do? Our society has advanced so much scientifically. You might look into the sky and see nothing but stars, but up there is one of the most important creations we've developed, the satellite. It helps us communicate, trade, travel, and advance as a society. But you may be wondering, how did that get up there? And why hasn't it fallen down yet?
In order to find out how fast our rocket must travel to leave Earth's atmosphere, we must find the kinetic energy of the rocket using the law of conservation of energy. This equation is the foundation of how our satellites can leave Earth's upper atmosphere and continue into orbit. It's a very simple equation. You could say it's not rocket science, or is it?
The kinetic energy of the system is the kinetic energy of the rocket plus the kinetic energy of the Earth in this equation. So because the mass of the Earth is so massive in comparison to the mass of the rocket, we can actually cancel out any velocity or kinetic energy of the Earth. So the total kinetic energy is actually just the kinetic energy of the rocket. To find the potential energy of the system, we're going to use Newton's equation for the law of gravitational potential energy. We are using the Earth rocket system's potential energy in the conservation of mechanical energy equation. Here's our rocket. Now, as we launch our rocket from the center, our potential energy is going to decrease as we get further and further away from Earth. This is U, G. And our kinetic energy is also going to be increasing as we are lifting off. These forces cancel out and makes the total mechanical energy equal to 0.
Didn't see you there. I think I got something to show you. Come. As you look at this diagram, you got to try to figure out what's going on. So as the rocket gets further and further away from Earth, the potential energy gets smaller and smaller. We want to get out of orbit, essentially infinite distance away from Earth, from where the gravitational potential energy is 0, and we will no longer be pulled down. On the surface of Earth, our potential energy is 0. That's because we're on the ground, right? And this is the graph of the potential energy in radius. At 0, the slope is undefined, therefore it's 0.
Find the escape velocity, which is the velocity needed for the rocket to exit the atmosphere and enter orbit, we need to use a conservation of energy, which is by adding gravitational potential and kinetic to equal 0. In order to simplify this equation, we would first need to move the gravitational potential energy to the other side. Now we're going to simplify the equation so we can get V. Now we have our equation for escape velocity. So you might be wondering, how does it work? So, we have a demonstration here. We have lid, our massive center object, and in this case, the Earth, and our satellite, represented by a marble. Now, this marble, just like a satellite, when released with enough, or the minimum velocity to get it in orbit, will orbit the center object, this golf ball. As you can see, it continues to orbit around and around. Once again. As you can see, the force or the velocity of this marble is enough to keep it spinning around this center object, and gravity is enough to keep it from flying away to a different part of space. And now in this demonstration, it's not perfect. The glass bowl might not be exactly how real life is in space, but it's as close as we can get. You can try it yourself using any shallow bowl, a massive center object like a golf ball, and a satellite, like a marble.
Multiple choice questions about what we just taught you. First question is, what is not a satellite? We have A, the moon, B, airplane, C, International Space Station, and D, space junk. The answer is B. Why? Well, an airplane is not in orbit. It's just flying. All right, next question. What is escape velocity? A, how fast the Earth moves. B, the speed of gravity. C, the speed of a rocket. D, the speed of the rotation of the Earth. The answer is C. Why? Well, the speed of the rocket that we just built escapes the Earth's atmosphere and returns to orbit. It requires escape velocity, and that's the speed of the rocket. Next question is, how does an object stay in orbit? A, it floats because there's no gravity. B, I don't know. C, it has a really big parachute. Or D, it constantly accelerates away from the Earth. The answer is D. Good job, guys. I have drawn up a table of the energies of our satellite in orbit. What do you think will happen to the energies as the radius from Earth increases? Which of these tables look appropriate? That's right. It's B. This is because the energies decrease proportionately.
Thank you guys for coming along with us on this journey to learn about rockets, satellites, and how it all works. Now, it affects us every day, and it will continue.